Good morning, ladies and germs, boys and squirrels. Welcome. We're going to be jumping into the next unit today. We are leaving physics behind. For fourth quarter, we are going to be in chemistry. So physical science is physics and chemistry, and we have done the physics stuff, and now we're moving into the chemistry stuff for the rest of the year. So we begin at the very beginning of chemistry concepts with atomic structure. What is the atom? How is it constructed? What did God put in there? And my little question: what makes up the stuff that all the stuff is made up of? And that's what we are looking at today. Okay. So where's I'll give you a moment to copy that down. Okay. So everybody knows that if you take, something, let's say you have a stick of butter, you cut it in half, you have 2 sticks of butter, right? You've got halves of a stick of butter. You cut that in half, you have quarters of a stick of butter. And you keep cutting it, and you keep going down to some point. Logically, there should be some point where you get to the smallest thing that can exist that is still butter. Where if you cut it in half again, it's not butter anymore. And that idea. So a long time ago, people were thinking about this idea for the first time, 500 BC, and a philosopher of science, a Greek philosopher, came up with the idea that everything was composed of irreducible components, and he did call them atoms. He's the one that came up with that name, and his name was Democritus. There you go, Democritus. But of course, he had no way of testing this, because 500 BC, they don't even have microscopes, much less, scanning electron microscopes, or things that will allow you to see very, very, very small. And so this was all just philosophical reasoning. And he wound up being right, that everything's composed up of these little tiny things. John Dalton, much, much later, John Dalton said that that all compounds exist in definite repeating ratios, and that was because matter was composed of atoms. So he went back and reinforced with some experimental data the ideas of Democritus. Of course, again, he didn't have any ability to visualize the atom, but he noticed that if you do chemistry and you're careful with how much of what things you add, it's always chunky. Chemistry always comes in pieces of things. And he reasoned, again, showing some chemical experimentation to support it, that there's chunks of stuff that everything is made up of, right? And he, again, used that word atoms. So the law of definite proportions is what Dalton was basing his ideas on. It was described by Joseph Proust in 1790, and Dalton was trying to explain that concept. So this is Dalton, and very famous for lots of things in science. Dalton came up with the first model of the atom, and he created Dalton's model, and he said that atoms cannot be created or destroyed in chemical reactions, that when you take an atom of carbon and you combine it with an atom of oxygen and you get carbon monoxide, that neither the carbon nor the oxygen change. They're still carbon and oxygen. It's just that when they're bound together, their properties change. And so he had this idea that atoms are not created or destroyed in chemical reactions. They're just recombined, right? And he said, and he's wrong, we've since discovered that number 2 is not correct. But he did say that atoms cannot be subdivided into smaller particles. You can't take an atom and cut it in half. Well, since then we've discovered that he's wrong. But he was right that if you take an atom and you cut it in half, you don't have half of an atom of carbon. You now have something else. And so atoms cannot be subdivided into smaller particles. That's part of Dalton's model. We've since said, no, sorry, just kidding. He says that elements are made up of only one kind of atom, and that is true. If you have pure copper, pure silver, pure gold, pure oxygen, pure nitrogen, then there's only one kind of atom in that element. And every time you find pure gold, it will be the same kind of atom as every other time you find pure gold. So these elements are made up of one kind of atom. He said that atoms of an element are all alike, and that is true. You don't have different sorts of carbon or oxygen or nitrogen or whatever atoms. You do have isotopes, and he didn't know about isotopes at this point, so we kind of have to qualify this idea as well. But as far as them all being made up of the same number of protons, that is true. Atoms of one element are different from others, especially in their masses. And so a gold atom is different from a silver atom, different from a copper atom. And the main thing that you can determine easily about these different elements is the kind, is their mass, the mass of those elements. And that'll become very important later in chemistry when we get to stoichiometry. In 2 years for you guys, you'll be caring very much about the mass of an atom. And that is one of the things that you can use to determine what kind of atom it is its mass. Okay, I'll give you a second because I think some of you are still waiting. Okay, so a little while later, another chemist with the last name of Thompson in 1897 did some experiments to demonstrate the existence of electrons. So they're kind of like other parts of the atom, there was a hypothesis that electrons existed for a long time. The Greeks even talked about the existence of some kind of negatively charged thing. And the word electron actually came from the Greeks, just like the word atom came from the Greeks. But they had no idea what it was, how it worked. And a lot of the experimentation to demonstrate the presence of electrons and how electrons functioned was done by Thompson in 1897. And he was able to come pretty close to determining the mass of an electron and the charge units of electrons and things of that nature. So he then added the concept of an electron to Dalton's idea of an atom and said an atom is actually this positively charged mass that has negatively charged things stuck inside of it. And he called it the plum pudding model. And we don't eat plum pudding very much here in Hawaii, but think of bread pudding. I've seen bread pudding a couple times here on the islands. Same idea. In bread pudding, you have this mushy mass, and there's usually raisins in it. And so you have raisins stuck somewhere in this mushy mass. He said that the atom is like that. The atom is this mass of positiveness with some electrons' negativeness stuck in there. No concept of a nucleus yet, no concept of orbitals, but he did say that there were positive parts and negative parts. And so it was called the plum pudding model. Okay?
Have you tried?
I'm sorry?
Have you tried bread pudding?
Oh, I love bread pudding. It's one of my favorite desserts. So this is Thompson. He looks like a, early 1900s or late 1800s scientist. And he is the one who came up with it. This is the plum pudding model, that it's mostly a positive stuff, and somewhere in there are negative things stuck. So this is plum pudding, and the little pieces of fruit in the pudding would be the negativeness, and the overall mass of the bready thing would be the positiveness. That's what he called it. Okay. Rutherford, just a couple years later, around 20 years later, clarified that it's not a mass of positiveness, that actually most of the atom is empty space. Most of the atom is a vacuum, it's nothing. That all of the positiveness is in this incredibly dense region in the middle, and he proposed the existence of a nucleus. And then he says the electrons are floating around the outside and leaving a lot of room in the atom that's empty space, with just electrons zipping around. So Ernest Rutherford in 1919 postulated the existence of the nucleus, some solid thing surrounded by electrons. And again, not too long after that, now we're looking at about 13 years later, in 1932, Chadwick discovered the existence of neutrons. Now, a neutron is also a part of the nucleus. So we knew that the nucleus was composed of positive things, and now Chadwick says, and there's also neutral things that don't have a charge in the nucleus as well. So the idea of what the atom is coming together by 1932. And this knowledge was starting to be formed not too long before we discovered how to break the atom. You know, the first atomic bombs started being tested, you know, within 10 years of this. And so once we discovered how it was made, we started figuring out how to break it. Let me give you just a second to finish writing here. So this is Rutherford and his apparatus. He was generating what are called cathode ray tubes, and he's shooting electrons around. And he was the one that was discovering that most of the atom is empty space, and this is his very cool apparatus, cutting edge in the 1920s, 19-teens. The model of the atom, the planetary model is what it was called, that he came up with, has electrons orbiting in circles around a nucleus of positive charge. And then Chadwick later helped us understand that the nucleus has neutrons in there as well. And we now know that the electrons don't orbit actually in circles. It's entirely a different shape, but we'll get to that in a little bit. This is Chadwick, looking very professorial, as he's sitting there for his headshot. Niels Bohr discovered that not all electrons orbited in the same distance from the nucleus, and he was the first one to use emission spectra, and I'll describe what that is in a minute, to determine electron configurations. And so he says, no, they're all at different distances from the nucleus. The nucleus is not the center of a circle of electrons. That the electrons are all laid out in different arrangements from the nucleus. And so he used emission spectra, and we will do a lab with this in a little bit. Not today, but we'll do a lab with this soon, where we excite different kinds of atoms by burning them, by putting them in heat. And they burn with different colors of flame. And the different colors of flame have to do with the electron configurations. When something burns, the color it gives off is a product of how its electrons are arranged. And so he used that concept to figure out, well, if these colors of light are being emitted, then that must mean that the electrons are in this arrangement. And he did a lot of work on helping us understand electron configurations. So Niels Bohr in 1922 creates the planetary model where they're all laid out at different distances from the nucleus. And so the model of the atom from him looks like kind of a picture of the solar system. It's okay. And here he is with his electron spectra, and we will see this kind of stuff in a lab. Not quite the same presentation. You'll do a lab just like this in chemistry, but in physical science, we're just going to look at different colors of flame as different things burn. But he was able to demonstrate different electron configurations based on the colors of light that elements gave off when they burned. Okay. And I know I have more. My mouse is not mine. There you go. So he came up with this idea where there are layers of electrons. So the nucleus in the middle, and then there's a shell next to that that can hold 2 electrons, and then there's a shell next to that that can hold 8 electrons, and then there's a shell next to that that can hold 18 electrons, and it keeps getting bigger as you go out. And he was able to demonstrate this again with those different colors of flame. It's amazing how much you can learn from the color that something burns. But this is the model of the atom that he produced. And it's almost the same model that we use today. We still definitely use the concept of shells and electrons in shells, but we've now discovered that they're not just orbiting in circles, that it's more complicated than that even. Okay, so let me give you a second to write this down. So when we're trying to wrap all this up and summarize what do we know about the atom now because of the work of all of these different people, when we look at an atom, in the nucleus of the atom, there are two kinds of particles. There's the proton and the neutron. The proton has a charge of +1, it's a positive charge, and it has a mass of 1 atomic mass unit. And then a neutron also has a mass of 1 atomic mass unit, but it has no charge, so it does not affect the charge of the atom. They are only there for mass, to weigh something. And then an electron, these orbit the outside layers of the atom, and they orbit in successive layers around the nucleus. They do not have mass to speak of. I mean, they do have a little bit of mass, but it's so small that we ignore it. It's itsy bitsy teeny tiny. Doesn't matter. You know, when you fly on an airplane, they need to know how heavy the thing is so they can get in the air. And so airlines estimate the average weight of a person and how many seats have been sold and the average mass of humanity on the plane, and then they limit the weight of your bags, right? Your bags can't be more than 40 or 50 pounds, and they know how many bags they've got, how much that weighs. Carry-ons, things like that. So they know about how much weight they have, but certain things they don't weigh. Like they don't ask you how much do your keys weigh, and you can only bring keys on the plane that weigh a certain amount, because at some point the mass is insignificant. The same kind of thing for the atom. When we look at how much the atom weighs, protons and neutrons are what have the significant mass. Electrons weigh so little that we ignore it. It doesn't matter. Okay. There are lots of different electron orbit tables and different kinds of data that you can get about electrons and their orbits, and we will care much, much more about that in chemistry. For right now, when you're looking through your book next week, and we're in chapter 16 with more detail, then table 16.1 gives you lots of different information about the different electron orbits. Electrons in the outermost shell are the only ones that are used for bonding. So when one atom comes in contact with another atom and they make a bond, it's only the electrons in the outermost layer that make that bond. Electrons in deeper layers just hang out and stay put. And so we call those ones valence electrons. Valence electrons are the electrons in the outermost shell of an atom. Those are the ones that atoms will give and exchange and share and pass around to create chemical bonds. Those are also the electrons that metals will share with each other to allow electrical current to happen. So the outside electrons are the ones that we care about the most for chemistry, and they're the ones that we're going to be focusing most on when it comes to chemical reactions. So here's just a picture of one way of looking at the current understanding of the atom. Protons and neutrons in the nucleus, and all of the mass of the atom is represented by the nucleus, but the volume of the atom is mostly represented by the electrons. So the mass is condensed into the center part of the atom, and the volume is represented by this mostly empty space cloud of electrons floating around. Okay, last slide. I'll give you a second to write that down. So when we look at an atom and we want to know what element does that atom belong to, there are lots of properties of atoms, but the one that determines the element that it belongs to, the element that it is, we look at the atomic number, which is the number of protons. So an atom that has 6 protons is carbon, and it doesn't matter if the atom has 6 neutrons or 8 neutrons or 6 electrons or 4 electrons. That'll determine other properties of that atom, but if it has 6 protons, it's carbon. And so everything that has 6 protons is carbon. And if it were to gain or lose a proton, It wouldn't be a carbon atom with 7 protons or a carbon atom with 5 protons. It would be something different, right? And so the number of protons is the atomic number, is the identity for the kind of atom that it is. Atomic mass is the sum of protons and neutrons. Protons and neutrons both have a mass of 1, so when you add them up, that's the mass of the atom. And we weigh atoms in atomic mass units, and that will become important later on. But we're just essentially counting how many protons and neutrons are there. And then an isotope is something that has the same atomic number but not the same mass. So as I just said, every atom that has 6 protons is carbon. And some carbon atoms also have 6 neutrons. We call it carbon 12 because it weighs 12 atomic mass units. It has 6 protons, 6 neutrons. But you can also have carbon 14, which has 8 neutrons and 6 protons. And carbon 14 is still carbon, but it behaves a little bit differently, and it has a different mass, and we call that an isotope. An isotope is an atom, Nico brought his baby class, is an atom that has a different mass than its friends, okay? And so it behaves a little bit differently. And that is it for an introduction to the atom. We'll be playing with this concept for a while. Are there any questions?